Okay, today still QR algorithm for the computation of all eigenvalues. Consider some special case today. Topic 1, line 5. When the matrix A is symmetric A. Second case, second topic. QR algorithm very expensive. How to reduce the computational cost? Okay, so this is a make some improvement. If I still have time, we turn to study solution of linear systems. Of course, those linear systems huge, okay, large size linear system. Solve solution of linear systems. Take a review about QR algorithm to compute all eigenvalues of a matrix. Yeah, take a review. The QR algorithm. Algorithm. Input a matrix. Input a matrix. Yeah. Input a matrix. Suppose the matrix is a real matrix. And also here a real matrix. Yes, maybe also compass matrix also works. But anyway, okay. Now follow for K is then okay. First set A0 is A. Then follow for K 0, 1, 2 until converge. Yeah, until convergence. Now perform QR factorization of matrix A. Yeah, AK is Q K RK. Yeah, where QK is an orthogonal matrix. What is orthogonal matrix? Definition is transpose on Q times Q is identity matrix. When a matrix satisfies this, has this property, we call the matrix orthogonal matrix. Yeah. And what is R? R is upper triangular matrix. Perform QR factorization. This is an AK. Now, the next A, AK plus 1 is reverse the multiplication order. RK, QK. Yeah, this is AK. Under some conditions, it can be proof. We can prove, okay? We can prove. It can be under some conditions. AK, this matrix. First, AK plus 1 and AK, they have same eigenvalues. How to see this? Okay. AK plus 1 is RK times QK. And this is a Q orthogonal. So Q K Q transpose. Okay. Transpose QK. Correct. QK, RK, QK, right? Because Q transpose times Q identity matrix. Okay, now, yeah, this is AK, AK, AK. So this is QK transpose AK times QK. This equation implies that if I move QK to right side, then QK transpose is equal to QK inverse. So this is a QK inverse AK QK. This equation says that AK plus 1 similar to AK. Yeah. If you can write some matrix as some matrix inverse times A times the matrix Q. Okay, then yeah. When two matrices, you can find some Q so that this equation is true. Then we call them similar. Similar matrices, they have same eigenvalues. Yeah. So conclusion, AK plus 1 and AK have same eigenvalues. Same eigenvalues. This is number 1. Number 2, under some conditions. Yeah, number 2. Under some conditions, we can prove as K approaches infinity, AK plus 1 will approach upper triangular matrix. Yeah, upper triangular. An upper triangular matrix, its eigenvalues are the entries along the main diagonal line. So we can read eigenvalues of the original matrix A, okay, by reading the main diagonal entries along of this upper triangular matrix. So find out all eigenvalues. Yeah, this is a review. Now, topic 1. Consider A is symmetric. Okay. Okay. Yeah. Okay. Okay. Topic 1. Okay. Special case. A is symmetric. Okay. Theoretically, a symmetric matrix can be written as Q orthogonal matrix. Yeah. Q is I. Okay. We can find orthogonal matrix Q so that A can be decomposed as Q times lambda diagonal matrix. Yeah. Diagonal. Yeah. Diagonal matrix. Times Q transpose. So this is a Q. Because a Q orthogonal, so Q transpose is Q inverse. Before I forget, this Friday we don't have class. This Friday is semester break. semester break. Right. We can find some orthogonal matrix, some diagonal matrix, so that this equation is true theoretically. The diagonal entries, okay, the entries in the diagonal line of lambda are eigenvalues. How about Q? The columns of Q are eigenvectors. The columns of Q are eigenvectors. And in this case, in this special case, go back to the QR algorithm again. In this case, the AK plus 1 in QR algorithm, AK plus 1 will, as K approaches infinity, approaches lambda, all eigenvalues, diagonal matrix, lambda diagonal, zero, okay, everywhere 0. Of course, SK approaches infinity. Then how to find Q? Q, easy, okay. There's a Q0, here. When K is 0, then we get Q0 times Q1 times Q2 times QK will approach this Q, SK approaches infinity. So when A is symmetric, this algorithm find eigenvalues at the same time find eigenvectors. This is actually I should put this as a remark, okay, remark rather than a topic. Now, second topic. This algorithm very expensive. How expensive? Here. Perform QR factorization. Okay. Floating point operations. How many? It is order n cube. Okay, order n cube. What is n? Size. Floating point operations. Compute QR factorization. Okay, say, think about it. Say, if n is 1, say, not big, 1 million. 1 million. Then how many floating point operations? 1 million is this. Then total floating point operations to fit. So 10 to 18. What is 10 to 18? I don't know. Bigger than billion. So this is a very large number. N is 1 million. If n is a billion, then so very time consuming. Okay? Maybe you need to wait for years, okay, for a QR analysis. Okay, now how to reduce, how to drop the computational cost. Right? Depends on cases. Okay. First case, when A is symmetric, how to drop the computational cost. Okay. Improvement. I want to make improvements. Okay. Case 1. Okay. A is symmetric, okay? Symmetric. Input a symmetric matrix, then send input a symmetric matrix. Before I perform the steps, let me do some pre-processing on the matrix A. Okay. Okay. How to call the process? Okay. Here. Okay. Before running the QR algorithm. Yeah. Try diagonal lines. Which is it? What it means? That means means okay the meaning meaning here. Yeah. Find Q. Okay, where Q is orthogonal such that Q transpose. How about don't use Q, okay? Because so many Q's. How about use according to the root, use U, okay? U, yeah. U transpose times U is okay? Such that U transpose A, U is T, okay? T, tri-diagonal matrix. T is a tri-diagonal matrix. What it means? Tri-diagonal, okay? This matrix diagonal, okay? Yeah. Diagonal. Tri-diagonal. Yeah. Main diagonal. Lower subdiagonal. Upper subdiagonal. Entries on these three diagonals may belong zero. I don't know. But other entries must be zero. Yeah. This is a tri-diagonal. Right. Yeah. Okay. Now find some U orthogonal matrix. Okay. Yeah. You can find what the U is from my notes. Okay. For the details, you can take a look at the book. Yeah. U orthogonal such that U transpose times A times U is T tri-diagonal. Right? Because of this property. Yeah. This implies that what? Implies U transpose is U inverse, right? Move U to the right side. So actually, this is what? This is a U transpose. Yeah. U inverse. Yeah. So T and A. So T and A symmetric. Okay. Similar. Yeah. Whenever a matrix is some matrix inverse times another matrix, second matrix times the matrix. Yeah. Whenever this equation is true, the two matrices are similar. Similar matrices have same eigenvalues. So A and T have the same eigenvalues. And now I apply QR algorithm to this T. Okay, find the eigenvalues of T. Yeah. Okay. Now, let me modify this, okay? Input matrix symmetric, okay? Symmetric. Symmetric, yeah, symmetric matrix. Okay, now pre-process. Pre-process, okay. Before I apply QR everything, okay, pre-process, okay. U transpose A, U is T, okay, T is tridiagonal. Now apply algorithm to T. Now this is a T0 is equal to T. Then T QR factorization. Then after we compute QR factorization, we reverse the multiplication order. Okay. Because T has only 3 diagonal lines, all other entries are zeros. QR factorization, very cheap. Okay, yeah. Instead, the floating point operations is order n. Very, very cheap, very fast. Hey, we have a question, okay? Yeah. QR factorization of orthogonal matrix, upper triangular matrix for symmetry, then RK times QK. The question is, this product is still tridiagonal? Tridiagonal, okay? Yeah, we need to keep, T, tridiagonal. It can be proved, okay? This product still tridiagonal. Tridiagonal, yeah. Theoretically, you can prove, okay? Yeah. Tridiagonal matrix, QR factorization, then reverse the product, okay? A new matrix, this new matrix still tridiagonal. So we can repeat this again and again. Yeah, so this pre-process step, very important, save a lot of one. So this after you get this, then the following computation super fast. Order n per iteration, just order n optimal operations. If the matrix is 1 million, then that means that it's just about 1 million optimal operations. Very fast. This is a case one, symmetric. How about the general matrix? Okay, second case. Case 2. A is general. Before run the QR algorithm on a general matrix. Before run QR, okay. Perform. Okay. Tridiagonalize matrix A. Now A is not symmetric. We cannot tridiagonal matrix A. Reduce. Okay. Reduce A to a Heisenberg matrix. Heisenberg. How to spell it? Heisenberg. Matrix. Okay. What is Heisenberg? which is here, Heisenberg matrix. Yeah. A matrix of the following form. Main diagonal line, sub-diagonal line. Yeah. Then below sub-diagonal line, all entries are zeros. How about this part? Upper triangular part. Can be non-zero, okay? Yeah, can be non-zero. Yeah. A matrix of this form is Heisenberg matrix. Say for example, yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Then here 0, 0, 0. 6, okay, 6. This matrix Heisenberg matrix 4 by 4 Heisenberg matrix. So before we run QI algorithm, okay, yeah, reduce matrix A to a Heisenberg matrix. That means find orthogonal matrix, okay, such that U transpose A times U is Heisenberg. Okay, here H. Okay, Heisenberg. A Heisenberg matrix. Heisenberg matrix. Again, because of this property, okay, that Heisenberg matrix is similar to A. So therefore, A and Heisenberg matrix have the same eigenvalues. Okay, now apply QR algorithm on H. Okay, yeah. Input a general, this general, okay, not symmetric. Yeah, a general matrix. Okay, now the process reduce A to Heisenberg H. Now apply QR algorithm to matrix A. Yeah, set H0 to be H. Now perform QR factorization on HK. Then reversely multiply Q and R to get HK plus 1. H. This matrix is not full, okay? Not a full matrix. Yeah, at least this part entries are zeros. And this part save zeros, save a lot of work. Okay. When we perform QR factorization on a Heisenberg, which is what is the computational cost? N squared. Okay. If the matrix is not Heisenberg, QR factorization is N cubed, N squared. Save a lot, okay? Yeah. N squared, N cubed. Huge difference when N is large. When it's 1 billion, okay? So this number greater than this number by 1 billion times. Okay? This is a huge difference. Same person. Heisenberg, QR factorization. Then this new H, still Heisenberg? Yes, still Heisenberg. So all H Heisenberg. Theoretically, we can prove Heisenberg QR factorization, then R times Q, still Heisenberg, still in this form. Pre-processing, okay, is common in computation. In computation. To apply an algorithm, okay, pre-process the data you have, then apply the algorithm. Very common. Very common. Greatly reduce the time, computational time. Second topic, okay, some improvement. I still have time. Now, third topic, solve linear systems. Right? Okay, Michael, do you have questions? Okay, now third topic, linear systems. Yeah. This is an eigenvalue. I'm done. Okay. Topic 3. Okay. Solution of AX is equal to B. Okay. A is a complex or real, it doesn't matter. Here, in practice, okay, in practice, A usually is usually large. How large? Billion, okay. When we solve differential equations, we transform differential equations into linear systems. Discretize differential equations, then we have linear systems. Yeah. The linear systems size is larger. Numerical solution to the differential equation more accurate. Okay. So usually, yeah, billion. Think about it. Very, very large, super large. Billion size, billion by billion. Large and sparse. What it means, sparse? Any idea? What it means? A matrix is sparse.
Zero entries.
Huh?
Zero entries.
Zeros. Many zeros. Yeah. Yeah. Non-zero entries is order n. Okay. N by n matrix. N by n matrix. If the matrix is full or dense, how many non-zero entries? N squared, right? So many, right? If the matrix is full, we call full matrix dense matrix. Think about that. N is a billion size. Billion, okay. Billion, 10 to 10 squared, then 10 to 20. Yeah. Your computer need to store so many non-zero numbers. Most of the computers don't have such big memory. But it's okay to store, order n, say billion. Okay, yeah. It's okay, okay. It's okay, 10 to 10. It's okay. We have memory to store so many. Sparse, very important, not dense. Okay. Well-known algorithm to solve a linear system is Gaussian elimination. You read, yeah, Gaussian elimination. Very popular, right? Gaussian elimination. Okay. 哎，GE has two steps. Two steps. Step one, LU vector matrix. A, yeah. Compute LU factorization. Where? What is L? L is lower triangular matrix. Yeah, see. U, upper triangular matrix. Hey, now step two. Hey, step two. We want to solve AX is B. Okay, now after we have LU factorization, then LUX is B, right? Now how about maybe denote this by Y? Okay, yeah. Denote this. Then we have LY B. Okay, and then UX is 1. Okay. Right, now step 2. So LY is B. Okay, first for Y. L lower triangular matrix. To solve this linear system, forward substitution. Do you agree? Forward substitution, yeah. Starting with the first equation, get y1, then plug in y1 into the second equation to get y2. Forward. This step is floating point operation. Is order n squared. Yeah, n squared is okay. Okay, fast, very fast. But this step, okay, LU factorization is order n cubed. Yeah, this step is very slow, very slow. Yeah. After we get y, then solve this equation for x. Okay, then solve UX is 1 for x. Yeah, to get the solution. Yeah. U upper triangular matrix. So backward substitution to get x. Okay. Floating point operations same. Okay. Floating point operations is order n squared. Yeah, this is a Gaussian elimination. Gaussian elimination works well for a dense matrix. For sparse and large matrix, nobody use Gaussian elimination. Yeah, in industry, okay, or even in your research, you don't use GE. What is wrong? What is wrong with GE? Gaussian elimination. The problem is here. Okay, yes. Usually sparse. Sparse. But L dense. U dense. Even though original matrix A is sparse. But U here, full, okay, full. Okay, full. After LU factorization, we need to keep L and U for step 2. Otherwise, we cannot solve the equation for y and for x. We need to keep, okay, after we complete this, keep, okay, keep How many non-zero entries? This is a 1/2 L n squared. Yeah, non-zero. This is a 1/2 n. So actually, the sum is n squared. So Gaussian elimination requires your computer have storage so much storage. This is too bad. Too bad. Yeah. Too bad. So a lot of people use GE to solve sparse linear system. Then what algorithms we use in industry and also in your research to solve a large and sparse linear system? Iterative method. Okay, yeah. Iterative method. To solve a large and sparse linear system, in a company, in commercial software, use an iterative algorithm. Why iterative algorithm? Storage is cheap. Store only the sparse matrix A and a few, very few vectors. Then you can run an iterative matrix. Sparse matrix, sparse. Storage is cheap. Why it is cheap? Most of the entries are zeros. Yeah, non-zero entry. Non-zero entries, how many? Usually, order n. 3 times n, 4 times n, order n. Order n. To store zero, I don't need to store zero because 0 times anything is 0. What I need is non-zero entries. Only store non-zero entries. In an iterative algorithm, many operations are in a product. Vector U transpose times V and matrix A times a vector. Only these two, operations. Sparse matrix times a vector. I just need to store non-zero entries. Non-zero entries times 1 entry of V. 0 entry times 1 entry of V, always 0. So I don't need to care, 0 entries. Storage cheap. This is the reason why people use iterative algorithm to solve large and sparse linear systems. They don't use GE. Monday we studied iterative algorithms.